Hello, my name is Zhimin. I'm now working for ByteDance and currently focused on virtualization related project. Today, I will share my topic KVM life upgrade with properly handling of pass-through device. Next, I will introduce it from the four aspects. With the development of technology, the VM had to be frequently updated and restarted to add security patches and new features. There are two existing live update methods to improve the cloud availability. KVM live patch and virtual machine live migration. However, they both had serious drawbacks. Kernel life paths cannot handle complex change. For example, change to persistence data structure. VM life migration cannot handle the pass-through devices, and it may be incur unacceptable load delays because live migration need to copy memory from the old QEMU to new QEMU. In this topic, I will introduce our live upgrade method. They can probably update the KVM and QEMU without interrupt customer VMs. There is difficult for VM live upgrade. How to handle the pass-through device during the live upgrade and minimize service downtime is a major concern of cloud providers. In this talk, we will analyze the requirements for the pass-through device handle and present how we follow those requirements to properly handle pass-through device in our KVM life upgrade implementation. In addition, we also optimize the startup and suspend of VM to decrease the downtime during the life upgrade. This is the framework for life upgrade. In order to life upgrade KVM, we modify KVM module and allow it to be compliant multiple modules named by KVM1 module, KVM2 module, and so on. The specific implementation is that we move most of KVM module function into KVM inter module. To load multiple copies of KVM inter modules, we associate all the original global variables in KVM module with KVM inter module and make all the global function local. In Linux, a device pass-through is enabled by VFO. During the life upgrade, we inherit the VFO connector from the old QEMU to the new QEMU. And the VM's memory is shared by the new and old QEMU process. The mapping from GPA to HPA is not changed during the life upgrade. And the IOMMU table and the IOMMU translation table is remain valid. So device DMA operation can continue execution without interruption, even when the VM is stopped. For pass-through device, how to ensure interrupt is not lost during the live upgrade. This is difficult. because pass-through device is not suspended. For this reason, the pass-through device interrupts can occur at any time. So we cannot complete copy the pass-through device interrupt from the old QEMU to the new QEMU during the life upgrade. There is an existing solution. Inject additional virtual ARQ is a core idea. First, new QEMU inherits VFIO event FDs from the old QEMU. Second, the new QEMU reads from event FD and receive the pending interrupts. In last, inject an additional virtual ARQ into the VM after handing over device. In this topic, we use post-interrupt technology to inject interrupt. Device will set a post-interrupt request bit where the device reading an interrupt. So we need only to ensure the same PI descriptor data between the old QEMU and the new QEMU process. We allow PI descriptor data is shared between the new QEMU and the old QEMU during the life upgrade. This picture shows PI descriptor data initialization compared to original KVM design. In order to share PI descriptor data in the new QEMU, we allocate memory for PI descriptor data structure in the QEMU. There are three key points for PI descriptor structure initialization in the new QEMU. First, PI descriptor data shouldn't not be initialized when the new QEMU is initialized. Second, the new QEMU don't need to seek post-interrupt requesting data from the old QEMU. Because PI descriptor data is shared between the new QEMU and the old QEMU. In last, the new QEMU don't need to update interrupt mapping table during the life upgrade. Next, I will introduce how to optimize the VM downtime during the life upgrade. This picture shows the life upgrade flow diagram. The first step, we focus children process and execute the new QEMU binary, and the new QEMU is initialized. The second step, we stop the old QEMU and save VM state. The last step, the new QEMU load state from the old QEMU and start the new QEMU. It is obvious that VM downtime contains the following phases. Stop the old QEMU, save the old QEMU state, load the state from the old QEMU, and start the new QEMU. When stopping the old QEMU, we find the cleanup event FD is taking a lot of time when devices have multiple queues. For example, net, block, and so on. The old QEMU process will be killed after the life upgrade. Under normal QEMU initialization lockage, event FD will be free by QEMU process. However, the device event FD will be free by the system if the QEMU don't free it. So device unit FD needn't to clean up by the AutoQEMU process while the life upgrade is successful. Other normal VM startup logic. First, event FD is initialized with the device startup. Then vCPU is resumed. So the VM downtime contains the initialization of device event FD in this way. Inspired by the optimization of VM suspend, we can pre-create the device event FD during the QEMU initialization because the VM downtime don't contain the new QEMU initialization. We can decrease the startup time in this way. In last, we use the shared memory to save the old QEMU state, and loading state in the new QEMU happens concurrently with saving state in the old QEMU. We use the different vCPU number and memory size to measure the vCPU downtime with the different workload. We use the different benchmark tools to simulate the common use case of the cloud service, including computation, storage, and memory. We use the following tools: streets, memory tester, and FIO to simulate computation, memory, and storage. This picture shows the distribution of vCPU downtime under the VMI idle. We can see the distribution of VM downtime is 11 milliseconds to 34 milliseconds. Next, we use the strings tools to simulate the competition workload. While running the street tools in VM, we update the VM in host, and we can see the distribution of VM downtime is 12 milliseconds to 34 milliseconds. For the memory tester, we use the memory. We use the memory tester tools. We use 4 GB memory in VM, and we observe we observe the distribution of VM downtime is 12 milliseconds to 34 milliseconds. In last, we use the FIO tools to simulate the storage workload. We read-write 14 GB to disk. We observed the distribution of VM downtime is 12 milliseconds to 38 milliseconds. Based on the above tester result, we find that the relationship between the vCPU downtime and VM workload were not close. Okay, that's all. Thank you for your listening my topic. If you any question for this topic, please contact me by this email. Thank you.